will kick you out of the room. And then, oh, I think it's okay. It has started the recording. So I'll share my screen. What's going on? Not. So you can see my screen? Hello?
Yes.
Yeah.
Yes.
Yeah.
We can see it.
Yes.
Just put it in presentation mode, then we can. I think we had done this yesterday. I think we had done all this. No, I don't think. Not that far. We stopped here, right?
Yeah.
Yes.
So have you tried to do number 2 and 3? Is there anyone who has tried this? If you can give the answer for number 3, you will get 100 MB of mobile data. But you have to be in Safaricom. Anyone answer for number 3? Hello, you can hear me?
Yes.
Oh, inaonekana nyinyi mko na bundles za kutosha bana, si ndio?
Yes, we have enough.
So I can keep my bundles. Okay. Try to do number 3 on your own. Then next time we shall you let me know how far you're.
Send me for free.
So you have to solve a problem first. So let us start with this theorem.
I can give the answer.
We've run out of time now, so let me just continue. We will go back to it later. Let G be a group and let A be an element of a group, G. So this theorem says that if A raised to n is equal to the identity element, where n is an integer different from 0, usually, then the order of A will divide n. Right? So the order of A, remember the definition, the order of A is the smallest positive integer such that A raised to that integer will be equal to the identity element in the group. So this first part says that if A raised to some integer is equal to the identity, some non-zero integer, then the order of A will divide that n. So the second part of the theorem says if the order of A is known and is equal to m, then for any integer, A raised to I will be the same as A raised to Ri. This is a remainder when R is divided by m. So for instance, if m is equal to 4, then A raised to 5 will be equal to A raised to 1, because if you divide 5 by 4, the remainder will be 1. So this second part can help you to compute large powers in a group. Once you know the order of an element, you can easily compute large powers of the element in the group. So this third one says if the cyclic subgroup generated by A is of order M, the cyclic subgroup generated by A is of order M if and only if the order of A is equal to M. This is wrongly stated. This first if should not be there. So the cyclic subgroup of G generated by A is of order M if and only if the order of A is equal to M. That's the correct statement. So we will prove each of these three statements. Just take time and look at them, make sure you understand what they mean. So we will pick the first one and prove it. Recall the first one simply says that if A raised to N is equal to the identity element, then the order of A must divide N. So let's have a look at that. So from the theorem, we have A raised to N will be equal to the identity. And let's fix the order of A to be equal to M, right? By the division algorithm, we will have, we'll be able to write N equals to MQ plus R, where R is strictly between, it can be 0, but cannot exceed M. So 0 is less than or equal to R, but it's strictly less than M. This is from the division algorithm. We did this in discrete mathematics. So this leads us to the following situation. You can rewrite A raised to N as A raised to MQ plus R. Then you can split the two into A raised to MQ multiplied by A raised to R. But we know that A raised to M, because the order of A is equal to M, it means A raised to M is equal to the identity. So this first term here will be equal to the identity, and that leaves us with A raised to R. So we have a small problem here. We have said the order of A is equal to M, but we have found a smaller integer R such that A raised to R is equal to E. But the way we define the order of an element, you can't find a smaller positive integer which when A is raised to that integer gives you the identity. So the only option for R is 0. If it is not 0, it contradicts the minimality of M. It means then the order of A will not be equal to M. So the only way this can happen, that A raised to R is equal to the identity, is if R is 0. So that's the only option. Now if R is 0, if R is 0, it means M will be a factor of N, because if you follow the division algorithm here, if the remainder is 0, it means M must divide N, or M is a factor of N. And that is what we wanted to show. And M happens to be the order of A, and therefore the order of A divides N. So we have proved the first part, that if A raised to N is equal to the identity, then this N here must be a multiple of the order of A. Any questions on this? So we move to the next. So you need to remember what the second one said. Maybe you can go back and read it again. The second one says if the order of A is equal to M, then if you raise A to any integer I, it will still be equal to A raised to this Ri, where Ri is a remainder when I is divided by M. Okay, so this is what we want to show. So once you know the order of an integer, of an element in a group, then you can easily compute any power of that integer. Sorry, any power of that element. Once you know the order of an element in the group, then you can compute any power of that element easily using this statement, where a raised to I will be equal to a raised to Ri, and Ri will simply be the remainder when I is divided by M. You can still hear me?
Yes.
Yeah.
Good. So here we go. So let's suppose that the order of A is equal to M. Then by the division algorithm, we have that for any integer I, we can write I is equal to MQ plus R, where again, M must lie between 0 and R. It can be 0, but must be strictly less than R. So let's see. The intention was to determine the value of A raised to I. So let's see if we can do that. So A raised to I is equal to A raised to MQ plus R. We simply replace I with this, and we can split that into AMQ and AR. But we already know that M is the order of A, so A raised to M will be equal to the identity element. So we have E, AR, and we're left with AR. But R is simply the remainder when I is divided by M, according to this statement here. So we have proved the part that A raised to I is the same as A raised to R, where R is a remainder when I is divided by M. Okay.
So I have a question.
Yes, Uliza.
Hapo kwa suppose the order of is equals to M in this equation, I equals to MQ plus R.
Yes.
Now, is it supposed to be M at the middle or R? Is R greater than or equal to 0?
Oh,
and
you
less
are
than
right.
M,
You are
or
right.
M is
Thank you very much. I didn't notice that mistake. You are right. This should be 0 is less than or equal to R, less than M. I did not even realize it was wrong. It's a remainder that should be smaller than M. R cannot exceed M. It can be equal to 0, but cannot exceed M. So there's a, yes, thank you very much. This is wrong. It should be 0 is less than or equal to R, less than M. Thank you. So, any other question on this part? So this one needs to be corrected. It should have R here and M at the end. So let's prove the third part. The third part, we can go back and read it before we prove it. The third part says that the cyclic subgroup of B that is generated by A will be of order M if and only if the order of A is also equal to M. So basically what we need to do, we have two things to check here. The first one is as the cyclic subgroup generated by A, assume that it's of order M, and show that the order of A will also be equal to M. So the order of a subgroup is the number of elements in the subgroup. I mentioned this earlier. You have to be really careful when talking about order. The order of a subgroup here will be the number of elements in the subgroup. So this statement says that number of elements in a cyclic subgroup will be equal to the order of the element, the order of the generator of a cyclic subgroup. So if A is a generator of a cyclic subgroup and it is of order M, then the subgroup, that cyclic subgroup will also have exactly M elements. Okay, so that's what we need to check. We will go to the proof now. So we start by taking A to be of order M, and then we proceed to show that if A is of order M, then the cyclic subgroup generated by A will have exactly M elements. So if we set A to the order of A to be equal to M, then we can show that these M elements, M, 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 M which are listed as a squared all the way to a raised to m minus 1, these m elements will be distinct. That's our first thing we can show. So to show that, we'll prove by contradiction. So if they're not distinct, then it means there must be two of them which are equal, with the I not equal to j. So suppose we have these two, ai is equal to aj, and I is different from j, and I and j are both between 0 and m. Then we can multiply both sides of this equation by the inverse of ai. So the inverse of ai is a minus I. We do that, and we can put these together to be j minus I. This is because j is bigger than I. That's why we have rearranged it that way. But the way it is set up here, it means j minus I must be smaller than m. So again, this is a problem for us because we have found a smaller element than a smaller integer than m, such that which is this j minus I, and aj minus I gives us the identity. So that cannot happen unless j minus I is equal to 0, because the smallest positive integer that's supposed to work in this case should be m. So j minus I is smaller than m, and therefore cannot give us the identity element unless j minus I is equal to 0. So that means in that case, if j minus I is equal to 0, it would mean j is equal to I. The only way they can be so if they are not distinct, it means they can't be different. ai must be the same as j. The only way ai is equal to aj is if I is equal to j, as long as I and j lie in this interval. So this will contradict the fact that I is not equal to j, and therefore these elements must be distinct, because when we assume that they are not distinct, we end up with a contradiction. So we have confirmed that these are all the possible powers of A, right? Any other power of A will coincide with one of these. We have shown that these are distinct. So what we need to show is that any other power of A will coincide with one of these. That's the next bit we will show. If we'll show that these are all the possible powers of A, then this will be the cyclic subgroup generated by A, and it will be of order M. So let's show that any other power of A will coincide with one of these. So if we already said the order of A is equal to M, then these elements are distinct. Oh, we have done that part. So the next part is this. Let's consider the cyclic subgroup generated by A. And from the previous bit, we saw that for any integer I, A raised to I is equal to A raised to Ri, where Ri is the remainder when I is divided by M, and therefore this Ri cannot exceed M, right? So you can't get anything outside these M powers, because this remainder I will lie between 0 and M, so it will be from 0 all the way to M minus 1, and therefore it can't give you anything outside these M powers. It doesn't matter which integer you pick. When you raise A to that integer, you will end up with one of these. So it means the cyclic subgroup generated by H will consist of exactly M elements. What we have shown is if the order of A is equal to M, then the cyclic subgroup generated by A will consist of exactly M elements. So the order of the cyclic subgroup generated by A is equal to the order of A. So we need to prove a converse. The converse now should be if the cyclic subgroup generated by A has exactly M elements, then the order of A will also be equal to M. So suppose H, the the cyclic subgroup generated by A is of finite order, then it's the if you raise A to I, then you will have to find that these powers of I will not be distinct for all integers. Otherwise, it will not be of finite order, right? If it's of finite order, then if you keep raising the generator to some integers, you will find some that are equal. So that means for some two integers, A raised to I will be equal to A raised to J, where I is not equal to J. So for this reason, it means we can show that A is of finite order. Why is A of finite order? Because now A raised to J minus I will be equal to the identity. We'll find an integer such that A raised to that integer is equal to the identity. So we confirm here that this tells us A must be of finite order. So we fix this order to be equal to M. Since it's finite, you must give it you can fix a value. And so then H will have exactly the same number of elements, which is M, right? As we had shown in the previous part. So if the order of H is finite, then it will be equal to the order of the element A, which generates H. Are there any questions on this? You can hear me?
Yes.
Thank you.
Yes.
So
Yes.
I believe that means there's no question.
Yeah.
So let's check the theorem. Let G be a group and let A be an element of G of infinite order. Then if you pick two integers, two distinct integers, I and J, A raised to I will not be equal to A raised to J. So if an element is of infinite order, then for any two distinct integers, I and J, A raised to I will not be equal to A raised to J. Just a minute. Is there any question on that? Is there any question? No. So keep that in mind. Then as a consequence, if G is a group of finite order, then every element of G will be of finite order. So you can try to prove these two. I have not done the proofs. So this is something you can try to do yourself. Try to prove this. So let's look at the next one. So this theorem says the following. If so let G be a group and let A be an element of G. Suppose the order of A is equal to n. Then for all m, all integers m, the order of A raised to m will be equal to n divided by the GCD of m and n. So if you know the order of A, an element in the group, it's possible for you to compute the order of any power of that element in the group. Is that making sense?
No,
Yes.
no, no.
So this, you see, this is A. We are trying to find out, if I want to find the order of A raised to M, A raised to M is a power of A, right? I have some information already. I know the order of A is equal to N. What I want to do is to find the order of A raised to M. So this theorem says that the order of A raised to M will be N, which is already known as the order of A, divided by the greatest common divisor of M and N. There's nothing special there. It's just, don't overthink this. Just take it easy. Have you understood now?
Yes.
Yes.
Okay, so we are finding the order of the elements in the subgroup.
Yes,
Because
it's the order of, yes. Continue.
because A raised to M is a member of A,
Of G.
of G.
A raised to M simply means you multiply A by itself A times. G is a group, and if you multiply anything in the group by anything in the group, you get something in the group.
Okay.
That one should be clear to you by now. We have done this, all the properties of a group. So don't leave them behind. Carry them with you, all those properties. So A raised to M simply means multiply A by itself M times, okay? So if you want, this is an element in G and you want to find its order. So it says if we know the order of N, we can easily find the order of A raised to M by simply dividing N by the greatest common divisor of M and N. That's all. We shall do some examples later. For now, let's focus on the theorem itself. So let's fix some notation. We say let D be equal to the greatest common divisor of M and N. So if D is a common divisor of both M and N, it means it divides both of them, M and N. So we can write M as a multiple of D. We can also write N as a multiple of D. So M prime and N prime are just positive integers. Now, if you pick, if D is the greatest common divisor, then M prime and N prime cannot have a common divisor bigger than 1. Otherwise, then D will not be the GCD. So in that case, we are left with a conclusion. We must have that the GCD of M prime and N prime will be equal to 1. Any questions on that? We will need that information later, so try to understand it. But that is fairly simple. D is a common divisor of M and N, so it means I can write M as a multiple of D. I can also write N as a multiple of D. And since D is a GCD, I can't have any M prime and N prime cannot have any common factor bigger than 1. If they do, then D will no longer be the greatest common divisor. You can find a larger common divisor. So that means the GCD, M prime and N prime must be co-prime. The GCD is equal to 1. I hope that is clear.
Yes.
Good. So remember, we're interested in finding the order of A raised to M. So let's fix R to be equal to the order of A raised to M. So if R is the order of A raised to M, it means if I raise this element power R, I should get the identity. That's just by definition. So this again is the same as A raised to MR. And this means that the order of A itself must divide MR. There is a theorem you've just done today. which says if A raised to some integer is equal to the identity, then the order of A must divide that integer, right? We've just proved that in case you don't remember. So this result we are using here is from the previous theorem we proved, right? So we can make this statement that the order of A must divide MR. And note the difference. We are talking about here, it's the order of A we are referring to, but here R is the order of A raised to M. Don't mix the two. So the order of A is fixed as N. If you go back to the theorem, you will see that we had fixed the order of A is equal to N. Yeah. So if order of A divides MR, it means MR can be written as a multiple of N because N is the order of A, right? So it means I can write MR as a multiple of N, where T is some natural number or integer, if you like. We can divide throughout by D. Remember, D is a common divisor of M and N. So we can divide throughout by D to obtain the following. If you divide M by D, you will get M prime. That is because that's how we defined M prime. So if you divide M by D, you will end up with M prime. Are we together? Similarly, if you divide N by D, you will end up with N prime. Now we know that the greatest common divisor of M prime and N prime is 1, right? So if N prime is a factor of M prime R, the only way that can happen is if N prime divides R, right? Am I right or am I right?
Yes.
Yeah.
Yes. So, and if that happens, it means N prime must be less than or equal to R. If N prime divides R, then it must be less than or equal to R. It can't exceed R. So we take that as our first statement. We shall use it again. Now this N prime is precisely the same thing as N over D, which is N over the GCD of M and N, right? Keep track of that. N prime is exactly this thing. I'll just go back to the theorem. This thing is N prime, the whole of this. So let's look at the next bit. If you have A raised to M, AM raised to N prime will be equal to AM raised to N. N prime is the same as N over D. Remember, that's how we defined N prime. So I can rearrange this power so that I have A raised to N, M over D. But I know the order of A is equal to N, so A raised to N should give me the identity element. So this A raised to N here is just the same as the identity element raised to M prime, which is equal to the identity element. So if we have the following, A raised to M, AM, A power M raised to N prime gives us the identity. So that means the order of AM must divide N prime, right? According to the theorem we proved earlier. So the order of AM, A raised to M, must divide N prime because A raised to M, or rather A to the power M raised to N prime gives us the identity. But we know the order of A raised to M was R. We fixed it to be R. And here it must divide N prime. And if R divides N prime, it means R must be less than or equal to N prime. So this gives us only one option, and that is that the order of A must be equal to R, and is equal to N prime. So this expression here, number 2, which says R is less than or equal to N, combined with the first one here, which says n prime is less than or equal to r, means that the two must be equal. Oh, sorry. So r must be equal to n prime because of those two inequalities. And we know that r is just the order of m, but n prime is the same as n over d, which is the same as n over GCD, the greatest common divisor of m and n, which is exactly what we were looking for. We have shown that there's a mistake here. This should be the order of a raised to m, not a. It should be a raised to m here. You can see here it's written correctly, but somehow I forgot to correct that here. So a raised to m, the order of a raised to m will be equal to r. It was already fixed earlier, and we have shown that r must be equal to n prime, and n prime itself is just n over d, and d is the greatest common divisor of m and n. So we have proved the theorem. Is there any question? Because Wally, you can hear me?
Yes.
Yes. Can you?
That is the only question to respond to.
Yes.
Okay, so we will stop there for today.
You want your eyes?
So take time and read this very carefully. So I shared some type notes, and at the end of each section in that type note, that set of type notes, there are questions which you can use for practice. So I hope you are doing that so far. And if you encounter any issues with the questions, you are free to reach out.
Yes.
So as much as you'd like us to continue, we have to stop. But if you have any questions, you can ask.